What if I told you that there is a place where every real number has a home? A place where -5 can stand next to -4, where 1 by 2 can live between 0 and 1, and where even a strange looking number like root 2 has its own exact position. Sounds impossible, right? Maybe not, because this place isn't a map of cities, it isn't a map of countries, it is a map of numbers. And you have probably seen it many times before. A simple line with a few numbers written on it, the number line. But here's the mystery. Is a number line really just a line? Or is it telling us something much deeper about mathematics? Today, we are going to investigate. We are going to ask questions. We are going to look for patterns. We are going to challenge what we think we already know. And by the end of this lesson, I want you to look at the number line completely differently. Because we are not going to use simply the number line. We are going to investigate it. So grab your notebook, get ready to think, and let's begin our mathematical investigation. Let's begin with the most basic question. What exactly is a number line? Imagine you are creating a map. You need a fixed reference point. In our number line, that reference point is 0. From 0, we move to the right. 1, 2, 3, 4, and so on. And to the left, -1, -2, -3, -4, and so on. But notice something very important. The space between consecutive numbers are equal. The distance from 0 to 1 is same as the distance from 1 to 2 and the same as 2 to 3. This is called an equal interval. So the number line gives us more than numbers. It gives us position and distance. And here is our first mathematical observation. As we move right, numbers increase. As we move left, numbers decrease. But here's where our investigation gets interesting. Does the number line contain only integers? No, we can place fractions, decimals, and even irrational numbers on it. So the number line is not simply a tool for counting. It is a model of the real number system. And today we are going to discover exactly how. Let's start with negative numbers. Imagine checking the temperature on a very cold morning. The thermometer shows -3 degrees Celsius. What does the negative sign mean? It tells us that the temperature is below 0. Now look at the number line. Negative numbers are positioned to the left of 0 and positive numbers are positioned to the right of 0. And 0 sits between them. Now let's investigate something that often causes confusion. Which number is greater, -2 or -5? Don't calculate and don't guess. Just look at the number line. Where is -5 and where is -2? Which one is farther to the right? -2, correct? Therefore, -2 is greater than -5. Why? Because numbers increases as we move to the right. So we can justify our answer. -2 is greater than -5 because -2 is located to the right of -5 on the number line. This is an important mathematical habit. In MYP mathematics, we don't only want an answer. We want to know. How do you know? And more importantly, can we justify it? Now, let's make our investigation more interesting. Look at the numbers 0 and 1. How many numbers are between them? You might immediately say 0.5. It's correct, but is 0.5 the only one? Of course not. We could have 0.25, 0.75, 0.1, 0.35, 0.625, and many, many more. Now let's zoom in. Look between 0.5 and 0.6. We can find 0.51, 0.52, 0.53, and so on. But let's go even further. Imagine we zoom in between 0.525 and 0.526. We can still find 0.5251, 0.5252, 0.5253, and countless others. So here's the surprising discovery. No matter how much we zoom in, we can still find more numbers between two distinct real numbers. There are infinitely many numbers between any two distinct real numbers. Think about that. You can always go one step further, one decimal place further, one fraction further, one level deeper. That's one of the fascinating properties of the real number system. Now it's your turn. Find three numbers between 1 by 3 and 1 by 2. But don't just write them. Explain how you know they are between the two numbers. That's the difference between simply answering a question and investigating mathematics. Now let's investigate fractions. We usually think of a fraction as a part of a whole. For example, 1 by 2 means 1 half. But there's another way to understand a fraction. A fraction can represent an exact position on a number line. Let's take the interval 0 to 1. Divide it into 4 equal parts. We get 0, 1 by 4, 2 by 4, 3 by 4, 1. And look at this. 2 by 4 is equal to 1 by 2. They represent the same point. So, equivalent fractions are not just equivalent calculations. They occupy the same position on the number line. Now, look at the connection. 1 by 4 is equal to 0.25, 1 by 2 is equal to 0.5, and 3 by 4 is equal to 0.75. The fraction and decimal are different representations of the same quantity. This gives us a powerful mathematical connection. Fraction, then decimal, then position. They are not three separate ideas. They are three ways of describing the same mathematical quantity. Now investigate this. If the interval from 0 to 1 is divided into 8 equal parts, where would 1 by 8, 3 by 8, 5 by 8 and 7 by 8 be located? Draw it, estimate first, then check. Can you justify your positions? Now we reach the part that might surprise you. We have placed integers, we have placed fractions, we have placed decimals, but what about root 2? Where would you put it? You might think it's a square root, so maybe it doesn't belong on the number line. But it does. Let's investigate why. Imagine a square with side length 1 unit. We want to find its diagonal. Using the Pythagorean theorem, d square equal to 1 square plus 1 square. So d square equal to 2, therefore d is equal to root 2. The diagonal has length root 2. Now we can transfer that exact length onto our number line. And we discover 1 is less than root 2 is less than 2. And its approximate value is 1.414. But the decimal does not end. It continues 1.4142135 and so on. And it does not repeat in a predictable pattern. That's why root 2 is irrational. But here's the important part. Irrational does not mean imaginary. Root 2 has a real, exact position on the number line. So mathematics gives us another beautiful connection. Geometry, then Pythagorean theorem, then root 2, then number line. This is exactly the kind of connection we want to notice when learning mathematics. Now let's investigate something that makes the number line reliable. Equal intervals. Look carefully. The distance from -2 to -1 is the same as 1 to 2. Each interval represents 1 unit. But what if we change the scale? Suppose each interval represents 0.1. Then we could have 0, 0.1, 0.2, 0.3, 0.4, 0.5 and so on. The spacing must still remain equal. And fractions work in exactly the same way. If you divide 0 to 1 into 4 equal parts, 0, 1 by 4, 2 by 4, 3 by 4, 1. Each step represents 1/4. So remember, equal intervals means equal distances. This might look like a small detail, but it's actually extremely important because the same idea appears in graphs, rulers, thermometers, timelines, maps, and many other mathematical models. Whenever we use a scale, we need to understand what each interval represents. Let's stop for a moment. We have investigated quite a lot. Let's see what we have discovered. Number 1. Numbers to the left of 0 are smaller, numbers to the right of zeros are greater. Number 2. There are infinitely many numbers between any two distinct real numbers. Number 3. Fractions and decimals can be represented as exact points. For example, 1 by 2 can be represented as 0.5. Number 4. Irrational numbers such as root 2 also have exact positions. Number 5. Equal intervals represent equal distances. And finally, the number line helps us represent, compare, order, estimate, measure, and justify. So now we can answer our original question. Is a number line just a line? No, it is a mathematical model. A model that helps us see relationships that might be difficult to understand using symbols alone. And that's the end of a number line investigation. But remember one final idea. Every number has a place from -5 to half to 0.75 to root 2. Every real number belongs somewhere on the number line. So next time you see a number, don't just ask what is it. Ask where does it belong? What can I discover about it? How can I represent it? And most importantly, how do I know? That's when mathematics become more than a collection of formulas. It becomes an investigation. If you enjoyed learning this way, subscribe to MathGo for more concept-based mathematics and IB MYP lessons. And follow the MathGo on Instagram for notes, short tricks, quizzes, and more. Until our next mathematical investigation, keep questioning, keep exploring, keep learning. This is MathGo. Understand the concept, don't just memorize it. Thank you.